In the previous section, we have seen how we can decompose a square matrix into triangular matrices with the Cholesky decomposition or in a diagonal matrix using Eigendecomposition. In this last section, we will see how we can decompose every matrix in whatever shape they have. This technique is called singular value decomposition and states that every matrix of shape m times n can be always decomposed in the form of A is equal to a squared matrix multiplied by this sigma matrix, which has the same dimensions as the original one, and the transpose of another square matrix called, with shape m times n. In this picture you can see their dimensions. But these three matrices are particular. U and V have columns vectors that are orthogonal. So the matrix is an orthogonal matrix. The sigma is an m times n matrix, but it has on the diagonal the sigma values which are equal or greater than 0, and elsewhere from the diagonal the elements are equal to 0. The matrix U is said to be the left singular matrix, and its vectors are left singular vectors. The matrix V is said to be the right singular matrix, and its vectors are right singular vectors. The sigma matrix, which is in the middle of the multiplication, is said to be the singular value matrix, and the values in its diagonal are said to be singular values. If m is greater than n, as it usually is, the matrix can be written in this form, which, from the definition, the sigma has elements that are 0 everywhere, but not on the diagonal, in which we have sigma 1, sigma n. This m times n submatrix is diagonal then. As we have previously seen on the Eigendecomposition, here we can represent the singular value decomposition. We start from the top left corner, in which we have a space described by the canonical basis. We then apply the square matrix V transpose, which from a standard basis transforms the vector using the eigenbasis in the 2D plane. We are in the bottom left corner, and we use sigma for scaling the vector, and we use sigma to map the 2D plane to the R3 3D plane. 3D space. Again, we need to represent the vectors using the canonical basis, so we apply the U matrix that brings us the vectors in the 3D space from the eigenbasis to the standard basis. The singular value decomposition is very similar to the Eigendecomposition, as you can see in these two formulas. The Eigendecomposition operates within the same vector space, where the same basis change is applied and then undone. That's why we see P and the inverse of P here. In the singular value decomposition, the transformation can map one vector space to another. and these two can be not equal. So the singular value decomposition involves two different bases, and these two are simultaneously linked together by the singular vector matrix sigma. In this slide, I want to highlight the main differences between Eigendecomposition and SVD. In particular, Eigendecomposition is only defined for square matrices, and it can be applied only if we can find a basis of eigenvectors. In singular value decomposition, we can always decompose the matrix A into U, sigma, and V transpose. Also, A can have any shape, m times n. The second difference is that the eigendecomposition, in the eigendecomposition, the vectors of P do not need to be orthonormal. So the change of basis is not a simple scaling rotation. In the SVD, instead, the vectors of P and U, by definition, are orthonormal. So they represent rotations. For symmetric matrices, we can see that the eigendecomposition equals the SVD. And also, we can always decompose a symmetric matrix into a diagonal matrix. Let's see a brief example of how can we interpret the singular value decomposition. Here we have a transformation from the plane to the 3D space. The matrix, the transformation matrix of this function is represented by this 3×2 matrix. This one can be decomposed in these three matrices using SVD. Let's see what it means doing all these three steps, these three matrices. So let's take a set of vectors in R2. We then apply the V transpose matrix. So what we are doing here, this is the result. We are doing a rotation on the 2D space. We then apply sigma. There's an error, excuse me. This is sigma, not D. We are applying sigma, which scales and the vectors and maps the 2D vectors in a 3D space. As you can see in these pictures, our vectors still lie on a plane, but the vectors are stretched by the singular values, and now the environment is a 3D space, not a 2D plane as before. Finally, we apply U, in which we rotate the plane in the 3D space. From a singular value decomposition, we can express a way to approximate matrices. But let's take a look to a generic, how can we write in a generic form the SVD. So we have the U matrix. Here we have the sigma with the sigma values on the diagonal, and then we have the V elements. Since these terms are all equal to 0, if A has rank R, so the first R column vectors are linearly independent, we can write A as the sum of sigma E times the multiplication between the vector UE and VE transpose. because elsewhere sigma is 0. The UEVE transpose is an m times n matrix as A. So we can write this multiplication between vectors as AE. Choosing a scalar k which is less than r, we can approximate the A matrix with this A at k matrix, which is called rank K approximation. Usually, when we talk about matrix approximation, we use the sigma values in descending order. So sigma 1 is equal or greater than sigma 2 and so on. So here in this sum we are taking the kth greatest sigmas. Let's see an example of what it means to approximate a matrix, and we can do it by taking a look to an image. We already seen in the first course, talking about linear algebra, that a computer sees an image as a tensor, a 3D matrix. In this case, since the picture, the original picture, which is in the top left corner, is white blank colored, the tensor reduces to a 2D matrix, since here we have just one color, one channel. In this slide we can see what it means to approximate the matrix. So if we take an rank 1 approximate, so we are using the greatest singular value, we get those results. But just taking 5 singular values, we get an image that is pretty close to the original one. And we are using a lot less information in the rank 5 approximation than in the original image. In the original image we have to store each of the pixels in the image. Here we have just, remember, to store the sigmas and these vectors, which have a smaller dimension. Now we want to measure how close the rank K approximation is between A. What we are saying is that we want to compute the distance between the two matrices. So, as we've seen in the course number 2, talking about analytic geometry, we need to define a distance, we need to define a norm. And to do so, we use the Euclidean norm defined for the vectors. Remember that A multiplied by a generic vector x is still a vector. So in here we define the norm of a matrix as the maximum value that this fraction takes, and this fraction is computed by the norm of the A times x divided by the norm of x. So the norm of A is determines how long any vector x can be at most become when multiplied by A. Given the matrix, we can compute the distance between two matrices. The Eckhart-Young theorem shows us how to quantificate, to qualify the difference between the error between the original matrix and the K approximation. In particular, here we can say that the norm here is the distance between A and the K rank approximation of the matrix A is equal to the singular value in position K plus 1. We are at the end of the journey of course number 3, and let's recap the relevant matrix decomposition concepts that we have seen since here. So we have talked about the determinant, which is a function that measures the way a linear map changes the parallelepiped volume and how the vectors are stretched and rotated. We have then defined the eigenvectors that let us understand better and easily the linear transformations. The eigenvectors represent the directions along which the linear transformation acts, simply by stretching or compressing or flipping those vectors. The eigenvalues are the factors by which the compression, the stretching or the flipping occurs. Finally, we have seen that the best way to simplify a matrix is to apply the eigendecomposition, which reduces the generic squared matrix into a diagonal matrix. However, the eigendecomposition is not always possible to apply. In the other cases, we have to use the Cholesky decomposition if the matrix is still squared, or singular value decomposition if the matrix is rectangular. So now, simplification. We've seen how simplification leads to a better understanding of how things works. So let's move on in the course number 4 and let's see how to measure the things that vary during space and time.